In Chapter 11, we're going to look at chi-square tests. Chi-square tests allow us to compare multiple categories of categorical variables. With two proportion tests, we can compare two categories. But with chi-square tests, we can compare multiple categories. So data is given in terms of counts of categorical variables, usually in a table form. So we're going to look at an example here where we have a company called PPG, which stands for Pittsburgh Plate Glass Company, which is a very old company that no longer just makes plate glass. Maybe they don't even make plate glass at all anymore, but they do make automotive paints which they distribute globally. And they have an interesting thing on their website. They have a graphic showing the most popular colors that are used worldwide in automotive paint. So for 2018, we saw here that white, the global distribution of colors was at 39% white, 17% black, 12% gray, etc. The other category just includes like neutral, blue, green, and other colors that are in very small amounts. Now, if we were to compare a sample of cars sold, new cars made and sold in the U.S. in 2018, what were the popular colors in the U.S. and how did they compare to the global colors? So we took a random sample of 250 new car purchases in 2018 using dealer records and found this color distribution out of the 250 cars. These are known in chi-square tests as the observed counts, the counts that we get from our sample. Now we also want to calculate what's called the expected counts. The expected counts are the counts for each category that we would expect to get if our null hypothesis was true, if, in this case, that the global distribution and the U.S. distribution of colors were exactly the same. And I guess I'm getting the cart before the horse a little bit, so let's actually look at the null and alternate hypothesis. So the null hypothesis is that the population distribution of new car colors in the U.S. in 2018 was the same as the distribution of car colors globally. The alternate is that they are different. So for the null hypothesis, we would expect 39% of our 250 cars to be white, or 97.5 of them. Notice the expected counts do not have to be whole numbers. As a matter of fact, if they are not whole numbers, do not round them. Leave them in decimal form. We would expect 17% of them to be black, or 42.5 cars, 12% of the 250 to be gray, or 30 cars, and so forth. And we can see that the counts do not line up with what we expect. The observed and the expected counts are clearly different. The question is, how much different do they have to be significantly different and not just random sample variation? So we're going to run a chi-square test to find that out. The conditions we have to check are very similar in the first two. We have a random sample of 250 cars, and 250 cars is certainly less than 10% of all new cars in the U.S. in 2018. Our third condition is that the expected counts are all greater than or equal to 5. And we have calculated our expected counts, and they are all greater than or equal to 5. Just as far as showing work on this, you must check and show the expected counts. Make sure you label them as expected counts so it's clear that they are the expected counts. It's often good to put them in table form. So that would be very good to put like white, black, gray, silver, red, other, and then expected counts, and then list the values. Now, as far as doing the test, there's what's called a chi-squared test statistic, which you would find at the very bottom of the last page of your formula sheet under the inference, under all of the different standard deviations in those tables. The observed counts are the number in each category observed in the sample, and the expected counts are the number in each category if the null hypothesis were true. So we're using our data up above, we can calculate observed minus expected squared divided by expected, and then that means add them all. So we have our 6 categories. We've done this for each category, and these are the different numbers that we would get for each of those. I've circled the 3 biggest, which we'll get back to later, why that's important. So our chi-squared value is the sum of those, what are called chi-squared cell components. These are each a component of one square. And notice this idea, the observed minus the expected, is we're finding out how big of a difference is. we're squaring those differences just like we squared the differences when we did standard deviation to make them all positive so that we can add them up and get a numerical summary of that amount of variability. We're dividing them by the expected value because, for example, if my observed was 2 and my expected was 4, then I would have so I square that value, I would have 4 out of 4, which is a bigger number than if, for example, my observed count was 102 and my expected was 100, and there was still a difference of 2, but I was dividing by 100, then 2 out of 100 is a much smaller number, or 4 out of 100 when you square it, than 4 out of 4. So the difference, so we're looking at the size of the difference relative to what we expect. So if we expect a really big number, a small difference is not going to make much difference. But if we expect a fairly small number, then that same size difference might be significant. The degree of freedom is just the number of different categories we have. In this case, we have 6 different color categories, including other, minus 1. So that's our degree of freedom. Now, using our test statistic, our degree of freedom, and our alpha level, in this case we're going to say alpha is 0.05, we can go to a chi-squared table. So I'm going to move a couple places over here and go to a chi-squared table. Where is my chi-squared table? Got to find it. Chi-squared table. There we go. In my chi-squared table, what I want to point out is our degree of freedom is over here. Here's our alpha level, and if we find where those the column and the row intersect, we see this number 11.07. This is known as the chi-squared critical value. This is the value of chi-squared that cuts off the tail in the right side of the distribution. Notice this is what a chi-squared distribution looks like. It's kind of a skewed thing. And the area to the right of this chi-squared critical value is the 5% alpha. So if I have a number bigger than 11.7 for my chi-squared test statistic, that means it's going to correspond to a p-value that is less than 5%. Okay, so let's go back and look here at the page where I was. I'm going to find my page again. Okay, so here's where I was. Okay, so let's take a look at how this information kind of plays out with the values that I got. Okay, so my chi-squared test statistic is 27.569. Here's the chi-squared critical value from the table. So everything to the right of this 11.07 would be 5% of the area under the curve. What's to the right of my test statistic is clearly much less than 5%. Now, how can we find that value? I can do what's called a chi-squared CDF. It's in the same place where you'd find normal CDF on your calculator, but you put in your chi-squared test statistic, infinity, and 5 degrees of freedom, and I got a very, very small p-value, which is definitely what we would expect. So we can say since 27.5689, which is the exact value of this, is greater than 11.07, the p-value for that chi-squared test statistic is going to be clearly less than 5%, and then we can calculate it this way. There's also a way to find all of this information on the calculator, which I will show you in a minute. Okay, now how do we do the conclusion? Well, since p is less than alpha, we reject the null hypothesis. We have convincing evidence that the distribution of car colors in 2018 for the U.S. was not the same as the global distribution of car colors. So very same kind of conclusion we always do. But now we want to follow up. If we reject, so this says do this only if you reject the null hypothesis, we do what's called a follow-up analysis. We want to say how in particular are they different? If they're not the same, how are they different? So what we want to look at is which specific cell components give strong evidence for the null hypothesis, or for the alternate hypothesis, I'm sorry. So which are the most different? So we go back and we look at our biggest cell components. These are the 3 cell components that contributed most to this large test statistic. So we go back up and look, how are they different? White is one of the colors that is different. Gray and red are the the colors that give the most difference. So what we look at is the observed count and the expected count. we expected 97.5 of our 250 cars to be white if the US was similar to global, but we only got 65. So clearly US drivers seem to prefer, do not prefer white as much as the global market does. We see fewer red and gray than we actually got in our observed. So our expected are less than our observed. So US drivers appear to favor gray and red more than their global counterparts. So we say, in particular, U.S. car buyers in 2018 preferred white less and gray and red more than the global buyers overall did. So this is our follow-up analysis. Now, if we were to do this test on the calculator, you're going to want to start by going back and looking at your observed and expected values, and enter the observed and expected values into a list on the calculator. I've already gone ahead and entered my observed and expected counts into the calculator. Notice that I put OBS for observed, but I put EXP counts. If you just do EXP, your calculator already has a function called EXP, so you can't use that as a variable name. So you have to add something to it. So that's why I did that. I'll let you pause if you need to add those in, but I'm going to go ahead and do the test. So you go to Menu, Statistics, Stat Tests, chi-squared goodness of fit test, my observed list, observed, my expected list, expected. My degree of freedom is 1 less than the number of cells, so that's 5. This tells me where the calculator is going to put the results. So notice here I did the test actually in the spreadsheet, which is perfectly fine. Here's the chi-squared value, which is the same one I got. Here's the p-value, which you can also get using chi-squared CDF, my degree of freedom, and here are my component list. If you hover over this, you get the same 6 numbers that you got, with a lot of decimal places showing, but the same 6 numbers that we got by hand, just calculating those cell component values. You can also do this on a calculator page, in which case it would display like this. And to find the values from the component list, go to the variable button, go to where it says stat component list and push enter, and then you can up arrow to that and you can scroll back and forth to see the different numbers in the list. So that's how you do a chi-square goodness of fit test. I'm going to show you one other variation of this, the random number problem, in a separate video.